Before everything we know, before stars, galaxies, or even light itself, there was silence. Not the silence of an empty room, nor the stillness of night, but something far deeper, the silence of nothingness. No matter, no energy, no space, no time, and yet, somehow, from that silence, everything was born. The universe, vast, ancient, and magnificent, had a beginning. But what does that truly mean? When we say the universe began, we are really saying that time itself began. Before that first moment, there was no before at all. It is an idea that resists imagination. Every story we know begins with something. This one begins with zero. For thousands of years, humanity has looked up and asked the same question. Where did all of this come from? Ancient civilizations answered with myths of gods and chaos, of cosmic eggs and eternal darkness. The Babylonians imagined the heavens born from a vast primordial ocean. The ancient Egyptians believed a god spoke the universe into existence. Across cultures and continents, one truth endured. There was a moment when everything began. Today, through the lens of science, we trace that origin back to a moment so small, so hot, and so dense that even the laws of nature collapse under its weight. A point beyond understanding, beyond physics, beyond everything. The Big Bang was not an explosion in space, it was an explosion of space itself. In a fraction of an instant, the universe expanded from something smaller than an atom to something larger than a galaxy. Time was born, light appeared, and the universe took its first breath. Now we stand at the edge of that first moment, asking the question that haunts every curious mind, what came before? If the Big Bang marks the birth of everything, what existed before creation itself? Was there another universe before ours? An endless cycle repeating through eternity? Or was there truly nothing at all? Not even time to hold the promise of a before. To explore this mystery is to journey beyond science, to the threshold where knowledge ends and wonder begins. And so our story moves forward toward the first light, the first breath, and the birth of all things. From stillness, from a point beyond all points, something emerged. Not wind, there was no air, but the breath of existence itself. A single, perfect, unimaginably dense state gave rise to a transformation that shaped all reality. This was not an event that happened within space. It was the creation of space, the opening of the cosmic stage upon which all history would unfold. Imagine the entire universe, every star you have ever seen, every galaxy beyond the reach of our strongest telescopes, every grain of sand on every world, every living soul, compressed into a volume far smaller than a proton, smaller than anything the mind can grasp. Here, language fails, mathematics breaks down, physics dissolves into paradox. This was a state of perfect symmetry, absolute unity, where everything that would ever exist was one. And then it happened. In a moment so brief that a lightning strike seems eternal by comparison, the universe was born. This is the Big Bang. Forget the image of a cosmic firework exploding into darkness. That is a human metaphor, and it falls short. What occurred was the expansion of reality itself. Every point in the universe began rushing away from every other point. Space, its very fabric, stretched and swelled at a pace that shatters intuition. In less than a heartbeat of time, less than we could ever measure, the universe grew from its subatomic origin to a scale larger than the Milky Way. This was exponential growth, a cosmic doubling repeated again and again before the first tick of any clock that could be recognized as time. This was the moment of creation, the moment time found its arrow, the moment space gained dimension, the moment pure potential became something. The perfect symmetry of the singularity shattered, replaced by a new reality, blazing hot and unimaginably dense. The energy present in that first instant contained the blueprint for every law of physics, every fundamental particle, every force that would shape the universe for the next 13.8 billion years. The birth of the universe was not a gentle dawn. It was a furious cry of fire, the loudest and most important event in all of history. From this primordial furnace, the long journey toward stars, planets, and consciousness began. The silence was broken, and the universe played its first powerful note. To understand this beginning, we must travel to a time so ancient it defies comprehension. Beyond all ordinary meaning of past and future, we must enter the Planck epoch. This was the earliest moment imaginable, beginning at time 0 and lasting only until 10 to the minus 43 seconds. A duration so brief that comparison to everyday life becomes meaningless. It is the smallest unit of time in which any change in the universe could occur, the first tick of the cosmic clock. In that unfathomable instant, the universe was hotter and denser than anything we can calculate. A single teaspoon of this primordial substance would outweigh all the galaxies in the observable universe combined. Space and time themselves lost their meaning. They became fuzzy, probabilistic, a quantum foam of ever-shifting geometry. The smooth space-time described by Einstein had not yet formed. Cause and effect blurred, past and future intertwined. This was a realm ruled by quantum gravity, a theory still unknown, meant to unite the very small and the very large. Quantum mechanics and general relativity were one. All four fundamental forces of nature were unified into a single, perfect force. Gravity, electromagnetism, the strong and weak nuclear forces. There were no distinctions. Light and gravity were the same. The force binding atomic nuclei was indistinguishable from the force lighting the stars. The laws of physics as we know them did not yet exist. They were hidden within this unified energy field, waiting for the universe to cool and expand. This epoch marks the limit of our knowledge. To ask what happened before the Planck time is to ask a question that modern physics cannot yet answer. Perhaps the very ideas of before and beginning do not apply here. Our journey backward must stop. Not because there is nothing to see, but because we lack the language to describe it. And when this first heartbeat of the universe ended, something extraordinary followed, a rapid, a violent expansion that would stretch reality itself and set the stage for everything to come. The Planck epoch was the universe holding its breath. What came next was its first exhale, an expansion that would shape the cosmos forever. However, gravity never truly sleeps. The faint regions of slightly higher density, those subtle imprints recorded in the cosmic microwave background and supported by invisible halos of dark matter, continue their slow, patient work. Over millions of years, gravity drew more and more material into these regions. Primordial clouds of hydrogen and helium grew heavier, thicker, and colder at their edges, even as their cores began to tighten. And when a cloud becomes massive enough, collapse is not a choice. It is simply what happens. As the gas fell inward under its own weight, pressure and temperature in the center rose sharply. The cloud squeezed itself smaller and smaller, and in doing so, heated itself like hands warming from friction. After a long, quiet fall, something like 100 to 200 million years of steady gravitational surrender, the densest cores crossed a threshold, around 10 million degrees. And at that temperature, a new kind of fire began. Under such crushing heat and pressure, hydrogen nuclei were forced close enough to overcome their electric repulsion. They fused, becoming helium. That fusion released immense energy and outward pressure that finally balanced the inward pull of gravity. The collapse halted, not because gravity weakened, but because the star had found equilibrium. A star had been born. These were the first stars in the universe. Population 3, unlike anything that exists today. They formed from almost perfectly pure hydrogen and helium, the simple elements forged in the first minutes after the Big Bang. They contained no metals, as astronomers call the heavier elements. No carbon, no oxygen, no silicon, no iron. And that absence mattered. Without metals to help the gas cool and fragment into smaller pieces, the first stars tended to grow enormous, perhaps tens, even hundreds of times the mass of our sun. They burned with a fierce blue-white brilliance, millions of times brighter than sunlight, but they lived fast, and they died young. Where a star like the sun can shine for 10 billion years, these giants lasted only a few million. And when their fuel ran out, they did not fade gently. They ended in the most violent way the universe could offer. Catastrophic supernovae, and in some cases, explosions so powerful they tore the star apart completely. Those first supernovae were not just endings, they were beginnings. In their final incandescent seconds, they accomplished what the Big Bang could not. The temperatures and pressures inside those blasts were high enough to forge heavier elements from lighter ones. For the first time, the universe was seeded with carbon and oxygen, nitrogen and silicon, iron and more, atoms essential for rocky planets and for life. Those new elements were hurled outward into interstellar space, enriching the surrounding gas clouds, changing the chemical destiny of the cosmos. In the most literal sense, we are descendants of those first stars. Every atom of carbon in your DNA, every oxygen atom you breathe, every iron atom in your blood was once made in stellar furnaces long before the sun existed. The shock waves from those supernovae also acted like cosmic drums, striking nearby clouds and nudging them into collapse. A second generation of stars formed, population 2, born from gas that now carried faint traces of the universe's first heavy elements. These stars were still massive by modern standards, but less extreme than the first giants. And as generations rose and fell, the universe slowly grew richer in metals, more complex, more capable of building intricate things. Stars did not form alone. Gravity gathered them into groups, clusters of stars, gas, and dark matter, bound together like drifting lanterns pulled into the same current. These early collections merged and collided, and forming the first proto-galaxies. Over hundreds of millions, then billions of years, those proto-galaxies met one another in a grand, chaotic dance, crashing, folding, and combining until they became the majestic spirals and giant ellipticals we see today, including our own Milky Way. The cosmic dark ages ended. The universe, once quiet and dim, began to shine, lit by countless young galaxies, each holding billions of stars. The vast cosmic web that had existed first as an invisible skeleton of dark matter was now traced in light, marked by luminous islands of matter where gravity had patiently done its work. And this is the deeper story of the Big Bang. Not only expansion and cooling, but complexity slowly emerging. The universe began in a state that was almost perfectly simple. Hot, dense, or uniform, a high-energy world with very little structure. But as it expanded and cooled, perfect symmetries broke again and again. Each phase change left the universe with more texture, more distinction, more variety. Forces separated, particles gained mass, quarks condensed into protons and neutrons, nuclei formed, atoms appeared, light was released, stars ignited, galaxies assembled, and woven into all of this is something even more intimate, time itself. In the earliest instance, space and time may not have been smooth, reliable backgrounds. They may have been quantum and uncertain, a restless foam where the arrow of time was not yet fully defined. But as the universe expanded and flattened, space-time became more like the steady stage we experience. 3 familiar dimensions of space and 1 direction of time. That direction, the arrow of time, connects to the second law of thermodynamics. In a closed system, entropy tends to increase. Entropy is often described as disorder, but more deeply, it is a measure of how many ways a system can be arranged. The early universe, despite its heat and violence, was remarkably uniform, and that uniformity corresponds to an extraordinarily low entropy beginning. It sounds paradoxical, but it matters, because a low entropy beginning means enormous room for change, enormous room for structure to form. As the universe expanded, gravity began gathering matter into organized islands, stars, galaxies, planets, and eventually life. Local pockets of complexity within a cosmos that overall moves toward higher entropy. The universe remembers the past but not the future because it began in a special, highly ordered state. Each moment that follows is part of the same unfolding, a steady drift from simplicity into richness, from smoothness into structure, from a near featureless beginning into a universe crowded with patterns. The great voids between galaxy filaments are not empty by accident. They are regions that began slightly less dense and over time were emptied further as their matter was drawn toward denser knots. The bright chains of galaxies are the triumph of gravity acting patiently on tiny initial differences. Small seeds grown into the largest structures we can see. Space, time, and structure were not simply given. They emerged. They evolved together. Space expanded, making room for structure. Structure formed, guided by entropy and gravity, giving time its direction. And time in turn provided the long duration required for gravity to build. We have followed this story for 13.8 billion years, through light from the most distant galaxies, through the temperature of the cosmic microwave background, through the abundance of the elements. We have built a coherent narrative from evidence, from an unimaginably dense beginning to a vast universe filled with stars and meaning. And yet, at the very edge of that knowledge, the story pauses once more. Because even after we explain what happened from the first fraction of a second onward, we meet the final question. Quiet, persistent, and almost impossible to put down. What happened at time zero? What started the entire unfolding? The question feels natural to us because our minds are built for sequences, cause and effect, before and after. past flowing into present and present into future. The word before is stitched into our language. But when we aim that word at the universe itself, we discover the universe may not share our assumptions. The Big Bang was not an explosion within time. It was, in a profound sense, the beginning of time. In Einstein's general relativity, space and time are not separate things. They are woven into a single dynamic fabric, space-time. This fabric is not the stage on which the universe plays out. It is part of the universe itself, stretching, curving, evolving. And at the Big Bang, that fabric may have a boundary. If time itself begins there, then asking what happened before the Big Bang may be like asking what is north of the North Pole. The question uses a familiar idea, north, but applies it where it no longer has meaning. And still, our intuition resists. We imagine a dark emptiness waiting for the Big Bang to ignite. But even an emptiness is a place, and waiting is something that requires time. So we arrive at the real challenge, letting go of the deepest assumption of all, that time is an absolute river flowing independently of the universe. Instead, time may be a feature that emerged along with space. Does that mean the question is a dead end for science? Not necessarily, because general relativity is not our only tool. To understand the extreme conditions near the beginning, we must also turn to quantum mechanics, the strange probabilistic physics of the very small. And in that realm, the hard wall of time zero begins to soften. Quantum theory forces us to rethink what nothing means. In everyday life, nothingness is absence, an empty room, a silent void. But at the deepest level, a perfectly static emptiness may be forbidden. One of quantum mechanics' central principles, the Heisenberg uncertainty principle, says that certain pairs of properties cannot be known with absolute precision at the same time. The most famous pair is position and momentum. But there is another pair even more haunting here, energy and time. In very short intervals, the energy of a system can fluctuate. The shorter the interval, the larger the possible fluctuation. And this is not merely a limitation of our measuring tools, it is woven into the fabric of reality. It means that even a perfect vacuum is not truly empty. Imagine a sea that looks perfectly still from far away. From a distance, it is glass, but seen up close, it seethes with motion. In the same way, the quantum vacuum is restless. On average, its energy may be zero, but moment by moment, it flickers. For a tiny instance, or energy can borrow itself into existence so long as it is quickly returned. And because energy and mass are interchangeable, those fluctuations can briefly take on form. Pairs of particles and antiparticles that appear from nowhere exist for a heartbeat of time, and then annihilate back into the vacuum. These are called virtual particles, ghost-like, fleeting, and they turn empty space into a bubbling sea of potential. This is not just philosophy. It leaves measurable fingerprints. One of the clearest is the Casimir effect. Place two uncharged metal plates extremely close together in a vacuum, and they attract. Not because of magnetism, but because the quantum vacuum between the plates is constrained. Fewer fluctuations can exist there than outside. The imbalance creates a tiny pressure that pushes the plates together. The vacuum, the closest thing we have to nothing, behaves like something. And that quantum revolution may be the key that cracks open the origin question. If nothing is not a classical void but a state rich with fluctuating potential, then whatever preceded our universe may not have been absolute emptiness. It may have been a quantum vacuum. No stars, no atoms, no time as we know it, yet still governed by quantum rules. And if such a vacuum can produce particles, even briefly, it invites a far larger question. Could a quantum fluctuation, a momentary loan of energy from the void, ever be large enough and last long enough to become an entire universe? It sounds too vast to belong to quantum physics, and yet that is the strange symmetry at the heart of modern cosmology. The laws that govern the smallest scales may also hold the key to the largest. The uncertainty principle hints that the boundary between existence and non-existence is not a sharp wall, but a hazy, probabilistic shoreline. In the Hartley-Hawking no-boundary proposal and in quantum tunneling scenarios often associated with Alexander Vilenkin, the universe need not be triggered by a prior event in time. Instead, it may arise as a quantum transition, an emergence from a state without classical space and time into a tiny, nascent universe that can then inflate, expand, and settle into the long history we know. But an immediate objection appears almost sacred: conservation of energy. The universe contains an immense amount of positive energy, mass energy locked in matter, the motion of galaxies, the radiation of starlight. If creation meant conjuring all of that from nothing, it would seem to violate physics' deepest rule. Energy cannot be created or destroyed, and yet the universe carries another kind of energy, gravitational energy, with a strange accounting. Gravity is attractive. To lift a book, you must add positive energy, stored as gravitational potential. But the gravitational field that binds masses can be treated as contributing negative energy. The more matter you gather into bound structures, stars, galaxies, clusters, the more negative gravitational potential is involved. And here is the remarkable point. When cosmologists consider the total budget, positive energy in matter and radiation balanced against negative gravitational energy, the sum may be, at least in principle, very close to zero. A universe that contains everything, and yet may cost, in net terms, almost nothing. If the total energy required to create a universe is essentially zero, then the origin story changes. A universe could, in a sense, arise without borrowing positive energy that must later be repaid. It would be like borrowing nothing at all. And in that strange case, the uncertainty principle no longer insists the fluctuation must vanish quickly. The door opens quietly onto the possibility of permanence. One way to picture this is through quantum tunneling. In the classical world, a ball rolled up a hill must have enough energy to reach the top. If it doesn't, it rolls back down. It cannot simply appear on the other side. But in the quantum world, particles do something astonishing. They can tunnel through barriers they do not have the energy to climb. Their wave of probability leaks through the forbidden region, giving a small but not zero chance of being found beyond it. Vilenkin and others have suggested that the universe itself may have done something analogous. Imagine a simple diagram, energy on one axis and the size of the universe on the other. The state of nothing, no space, no time, corresponds to a point of zero size, and in this idealized picture, zero energy. To become a universe, there may be a barrier, a hill of conditions that must be crossed before expansion can begin. Quantum tunneling proposes that the universe could pass through this barrier. not by climbing over it in the classical sense, but by transitioning through it as a quantum event. In this view, the universe does not begin because something caused it before it existed. It begins because quantum laws allow such an event with a probability that is not zero. The Big Bang becomes not the origin of the laws of physics, but one of their consequences. The question shifts, not why did the universe begin, but how could such a beginning be allowed and how likely was it? And that leads to a thought even more unsettling in its quiet logic. If a universe can form this way once, why only once? Quantum mechanics is probabilistic, but relentless. If an event is possible, then given enough opportunity, it will happen. And if the underlying arena, the quantum vacuum, is limitless, creation may not be a single rare miracle. It may happen again and again. This is one path into the multiverse, not the science fiction version with portals between near-identical worlds, but a deeper picture emerging naturally from inflationary cosmology. Inflation proposes that the early universe underwent a brief phase of runaway expansion, explaining its smoothness, flatness, and the origin of galaxies. Yet when physicists examine inflation closely, many models reveal a striking consequence. Once inflation begins, it may be extremely difficult to stop everywhere at once. Instead, inflation may be eternal. Imagine a vast ocean of high-energy inflating space, a background sometimes called the false vacuum. In most regions, space continues to expand faster than light can cross it, not because anything moves faster than light, but because space itself grows. Quantum fluctuations ripple through this ocean, and in scattered regions, inflation ends locally. When it does, its stored energy converts into a hot, dense fireball, an event that, from inside, looks like a big bang. In this picture, our universe is just one bubble of space-time. While it cools into stars and galaxies, the surrounding ocean keeps inflating. More fluctuations occur, more bubbles form. Each is a universe with its own Big Bang, forever isolated as the space between them expands too quickly for contact. Creation becomes a process, not an event. This view reshapes our place in the cosmos yet again. Eternal inflation suggests our entire observable universe may be one region among countless others. And it offers a possible explanation for one of physics' deepest puzzles, apparent fine-tuning. The laws and constants of nature seem delicately balanced to allow complexity. Slight changes could make stars unstable or atoms impossible. Why do the numbers work? The multiverse offers a statistical answer. If many universes exist, each with different constants, most would be sterile, but a few by chance would permit complexity, and observers can only arise there. We see a life-friendly universe not because it was designed for life, but because only such a universe can be observed. What looks miraculous becomes inevitable. Yet this is not the only challenge to a single absolute beginning. There is another family of ideas, older in spirit, newer in mathematics, that envisions not endless branching, but endless return. A cyclic cosmos. In this view, the Big Bang is not the birth of everything, but the start of the current chapter in an eternal sequence of expansions and renewals. Early scientific versions imagined a big crunch, where gravity eventually halts expansion and reverses it, collapsing the universe into a final singularity that might bounce into a new beginning. But observations in the late 1990s changed the picture. The universe's expansion is accelerating, Dark energy appears to be pulling space apart, making a simple Big Crunch unlikely. The future, at least in this straightforward view, looks like endless expansion, colder, darker, and emptier. Yet even that does not kill cyclic ideas. It simply forces them to become stranger. Some of the most prominent modern cyclic models emerge from advanced theoretical frameworks like string theory and M theory. Ideas that suggest reality may have more spatial dimensions than the three we experience. In these pictures, our entire visible universe could be a kind of three-dimensional brain floating within a higher dimensional space, sometimes called the bulk. In the ekparodic or cyclic model proposed by Paul Steinhardt and Neil Turok, our brain is not alone. There may be another brain, another universe, moving through the higher dimensional bulk. Over immense spans of time, the two brains drift apart and then, through forces acting across the extra dimension, are slowly drawn back together. When they collide, the collision is not a localized explosion in ordinary space. It is an event that happens everywhere at once within our universe. The kinetic energy of the impact is transformed into a hot, dense plasma of matter and radiation, resetting conditions to something like a new Big Bang. After the collision, the brains separate again. The universe expands, cools, forms stars and galaxies, perhaps life. Over trillions of years, dark energy makes space sparse and cold, and then, in the far future, the slow pull begins again. The approach, the collision, the renewal. In this vision, time does not have a single starting point. It stretches indefinitely into the past and indefinitely into the future. The universe has no unique first moment where the laws fail. Instead, reality is a rhythm, expansion, emptiness, return, again and again. And somewhere within that rhythm, within one cycle, inside one brief window of warmth and light, there is us, listening, wondering, trying to understand how anything exists at all. Cosmic history, in this view, is not a straight line. It is an endless sequence of cycles. Each collision wipes the slate clean and begins again, another universe, another era, while the deepest laws remain the same beneath the reset. This picture of eternity is profoundly different from the eternity of eternal inflation. In the inflationary multiverse, creation is parallel. Countless universes branch into existence side by side, potentially with different effective laws and constants, all coexisting within a wider inflating background. In a cyclic universe, creation is sequential. There is only one universe, our universe, reused, renewed, and reborn again and again along a single thread of time. The first moment problem is solved by removing it. The universe has no ultimate beginning because it is always somewhere within its rhythm, always expanding or cooling or emptying or approaching the next renewal. Dark energy, in some versions of the cyclic picture, is not an inexplicable cosmic add-on, but part of the mechanism itself, connected to the slow dynamics that bring the brains back together and set the stage for the next collision. And instead of inflation, the model proposes a different route to smoothness and structure, a universe that is prepared by an ultra-slow contraction or an ekparodic phase, then reset into a hot beginning by impact. It is a grand and haunting vision, a cosmos with no dawn, no first page, only the endless pulse of creation and destruction, the cosmic heartbeat echoing through eternity. And here we find ourselves at a crossroads. We have traveled beyond the edge of what can be directly observed and into the domain of pure theory, ideas that stretch the human imagination to its limits. We have met two radically different eternities. Each replaces the simple, linear story of one beginning with something larger, stranger, and more mysterious. In one direction lies the multiverse of eternal inflation. Creation is unstoppable, ongoing, and distributed. Our Big Bang becomes one local event inside an endlessly expanding metacosmos, a single bubble forming in an infinite ocean. In that picture, reality may be unimaginably diverse. Every physically possible set of laws could exist somewhere, in some bubble, in some far region we will never reach. Our universe is not special, only one of the rare ones in which complexity can take root. In the other direction lies the cyclic universe, given modern form through brain collision models. Here, creation is rhythmic. Our Big Bang is not the beginning. It is a transition, the latest renewal in an infinite sequence of deaths and rebirths. One universe endlessly remade, a kind of cosmic phoenix rising again and again from its own ashes. And in their own ways, both pictures dissolve the old paradox. Both replace the question, what happened before time, with a framework in which time, or at least creation, has no limit. If the multiverse is true, the apparent fine-tuning of our universe may not be a miracle in need of a special explanation, but a statistical outcome. With enough universes, some will naturally have life-permitting conditions, and observers will only ever awaken in those rare pockets. If the cyclic picture is true, then the Big Bang is not an absolute origin, but the last time the cosmic clock was reset. The state before is not nothingness, but either an eternal quantum vacuum or an earlier phase of the same universe. And yet, we must be honest. At present, we do not know which, if either, is true. These ideas sit at the frontier of physics, often beyond direct verification. They may be beautiful mathematical structures that do not correspond to reality, but they are not arbitrary fantasies. They grow naturally out of our most successful theories, extended into regimes we cannot yet probe. And they reveal something quietly important. Science is not afraid to look at the largest questions. It does not promise certainty where certainty is impossible. It offers models, coherent, disciplined ways of imagining what might lie beyond the horizon of the measurable. In this far country, the firm ground of experiment begins to soften beneath our feet. The scientific method, our most powerful engine of knowledge, depends on observation, test, and the possibility of being wrong. A theory earns the name scientific by making predictions we can, at least in principle, check. But how do we test what happened before time began? How do we observe other universes that, by definition, may never be in causal contact with ours? How do we find evidence of a previous cosmic cycle if our own Big Bang erased every trace? This is where science, as it currently exists, meets a natural boundary, not a failure in honesty. Science can report what can be measured and what can be logically inferred from measurement. But when we ask questions like, why is there something rather than nothing? Or what is the purpose of the universe? We may be stepping beyond physics, beyond how and into why. We arrive at the shoreline of a vast unknown, where our tools are no longer telescopes and particle accelerators, but philosophy, introspection, and wonder. Here we confront the limits of our own minds shaped to survive in 3 dimensions, inside a linear flow of time, trying to grasp a reality that may have no beginning and no end. This is not a retreat from knowledge. It is a deeper engagement with it. It is the admission that the universe is not only a problem to be solved, but also a mystery to be experienced. And from this edge, one more approach emerges, one that may feel in a strange way both more elegant and more philosophically complete. It was shaped by one of the most influential minds of our era, Stephen Hawking, working with James Hartley. Their idea does not claim the past is infinite. Instead, it redefines what beginning means. This is the no-boundary proposal, a universe that is finite in time, yet has no beginning, no edge, no boundary, and no moment of creation in the ordinary sense. To understand this, Hawking offered a simple analogy. Imagine you are an explorer walking across the surface of Earth. You travel south and keep going, across oceans, across continents, until you reach a unique point, the South Pole. Now ask the question, what lies south of the South Pole? The question breaks. It becomes meaningless, not because there is a wall, but because the rules of direction change there. From that point, every direction is north. The surface of Earth is finite, but it has no boundary. The no-boundary proposal suggests the beginning of the universe is like that. A special region where the usual rules shift, but not an edge. To make sense of it, we must rethink time itself. In everyday life, time feels like a one-way line. But near the extreme conditions of the early universe, where quantum gravity may dominate, the nature of time itself may change. In the no-boundary picture, what we call time behaves more like a spatial dimension close to the beginning. Imagine the universe not as a sharp point, but as a smooth, rounded shape. In the standard Big Bang story, tracing backward leads to a singular tip where equations fail. In the no-boundary model, that tip disappears. The geometry closes gently like the rounded end of a sphere. No edge of space-time, no singular moment. The beginning becomes a smooth region where the time direction fades into a purely spatial geometry. There is no before, just as there is no south beyond the South Pole. The universe does not burst into existence within a pre-existing timeline. The timeline itself emerges smoothly from a timeless geometric state. In this view, the universe is self-contained. It is not created from something else and does not require an external cause. It simply is, explained by the internal logic of physical law. This represents a profound philosophical shift. For thousands of years, origin stories have searched for a first cause, a creator, a prime mover. The no-boundary idea removes the need for such a trigger, not by denying meaning, but by reshaping the question itself. As Hawking put it, the boundary condition of the universe is that it has no boundary. The proposal is not without challenges. It relies on quantum gravity, still incomplete, and on mathematical tools like imaginary time, whose physical interpretation remains debated. Yet its conceptual power is striking. It offers a finite past without a paradoxical first moment, a quiet, smooth beginning where before does not apply. This, however, collides with one of our deepest instincts, causality. From childhood, we learn that everything happens for a reason. Cause precedes effect. This principle underlies logic, science, and storytelling itself. To ask about the universe's origin is, in many ways, to search for the first cause. For over 2 millennia, philosophers grappled with this. Aristotle argued that causes cannot regress forever. There must be an uncaused cause. This idea shaped classical cosmological arguments. Everything that begins to exist has a cause. The universe began to exist. Therefore, the universe has a cause. It feels almost unavoidable. And yet, when applied to the universe as a whole, intuition begins to fail. What if the first premise is wrong? What if not everything that begins to exist must have a cause? At least not in the classical sense. Quantum mechanics complicates the picture. At the smallest scales, causality is no longer clean. Some events appear fundamentally random. Radioactive decay is the clearest example. We can predict half-lives with extraordinary precision, yet no theory can tell us when a specific atom will decay. There is no hidden clock. According to our best science, it simply happens. If classically uncaused events exist at the deepest level of reality, an unsettling question follows. Could the universe itself be such an event? In quantum origin scenarios, the universe does not arise from an earlier moment in time, because time does not yet exist. Its appearance is probabilistic, governed by quantum rules rather than classical cause and effect. In this way, the universe does not violate the first cause argument so much as evade it. Its beginning is not the kind that argument assumes. This creates a deep paradox. Causality allows science to function, yet when applied to the universe as a whole, it collapses in on itself. If everything needs a cause, what caused the first cause? And if the first cause can be uncaused, why not the universe? The models we've explored, no boundary, quantum tunneling, eternal inflation, suggest a shared possibility. Causality may be emergent, a rule that works beautifully within space-time, but not at the origin of space-time itself. Like up and down, losing meaning in free fall, causality may be local, not absolute. This is deeply unsettling. It hints that the universe may not have a reason in the way we demand. It may be the final brute fact, the foundation from which all explanations arise. Or perhaps our idea of causality is simply too limited. Some thinkers speculate about a different kind of causation, not temporal, but logical or global, where the universe exists because the whole structure is internally consistent, perhaps even with its final state influencing its beginning. These ideas remain speculative, but they reveal something crucial. The question of cosmic origins forces us to question our most basic assumptions. And as we move beyond established physics, we encounter an idea even more radical, one that challenges a cornerstone of modern science itself. For centuries, science has largely assumed physicalism, that reality is fundamentally matter and energy, and that everything else, including life and consciousness, emerges from their arrangements. In that view, consciousness appears late in cosmic history, a byproduct of billions of years of blind evolution on a small rocky world. But what if that assumption is inverted? What if consciousness is not something that appears only after the universe becomes complex, but something present, however faintly, from the very beginning? What if it is not merely a property of matter, but a basic ingredient of reality, as fundamental as space, time, or energy? This intuition lies behind views such as panpsychism. It does not claim that rocks or stars think like humans. Rather, it suggests something subtler, that the fundamental constituents of reality may possess a primitive form of experience, a minimal inside, however rudimentary. In this view, all human consciousness is not a miraculous spark emerging from entirely non-experiential matter, but a complex organization of simpler experiential elements that were always there. This may sound mystical, but it has returned to serious philosophical discussion largely because of the hard problem of consciousness. Some problems in neuroscience are difficult but tractable in principle. How the brain processes information, integrates senses, and controls behavior. The hard problem is different. Why does any of this processing feel like anything at all? Why is there subjective experience, color, pain, joy, attached to physical activity? Nothing in our physical theory seems to imply that matter should have an inner life. Panpsychism attempts to bridge that gap by proposing that experience does not suddenly ignite from nowhere. It was present in simpler form from the start. This opens a striking possibility for cosmology. If consciousness is fundamental, then the universe was not mindless for 13.8 billion years until humans appeared. Instead, reality may have carried an inner dimension from the beginning, however primitive and unified. The primordial plasma of the Big Bang would then be not just a blind storm of particles, but also, speculatively, a universe of the simplest forms of experience. This idea finds a provocative echo in the work of physicist John Archibald Wheeler. Troubled by the role of the observer in quantum mechanics, Wheeler proposed a participatory universe. In quantum theory, systems exist in superpositions until observation fixes an outcome. Wheeler wondered whether, on a cosmic scale, the universe might help bring about its own definite history through observation via a vast feedback loop stretching across time. Conscious beings emerging late in cosmic history might in some sense participate in giving the early universe a fixed past. This is not mainstream physics. It borders on metaphysics. But it reflects a serious attempt to grapple with the deep puzzles linking quantum theory, cosmology, and observation. It suggests a universe that is not a cold machine, but a dynamic process in which conscious beings are not just spectators, but participants. If even part of this is true, then the birth of the universe is not only the beginning of space, time, and matter. It is also the beginning of experience. The Big Bang becomes the first step in a long evolution of awareness, one that leads to stars, planets, and eventually beings capable of wondering where they came from. The universe is not just where we live, it is a process becoming aware of itself. Our scientific search for cosmic origins is recent, but the human urge to understand creation is ancient. Across cultures and millennia, we have told stories to answer the same questions. Where do we come from? Why are we here? Creation myths, whether literal or symbolic, express a desire to place our brief lives within a larger, enduring reality. Viewed through modern cosmology, some of these stories reveal striking resonances. Many traditions speak of creation from emptiness or unity. Genesis describes a formless void. The Quran speaks of heavens and earth once joined. Eastern philosophies imagine endless cycles of creation and renewal. Taoism describes an emptiness rich with potential from which all things arise. These are not scientific theories, but they're themes. Emergence from nothing, cycles, complexity from unity. Echo ideas we now explore with equations and telescopes. It would be wrong to equate ancient metaphors with modern physics, but it would also be wrong to dismiss them. They remind us that long before particle accelerators, humans were already reaching toward the same fundamental intuitions. Science is a powerful way of understanding how the universe works, but it does not settle every question of meaning or inner experience. Reflecting on older traditions connects our modern inquiry to a deeper human longing, not only to describe the cosmos, but to belong to it. And so we arrive at the final question. What, if anything, happened before? The most honest answer is the most humbling. We do not know, and we may never know, not in the way we know that Earth orbits the sun. The origin of the universe may lie beyond experimental reach. Acknowledging that ignorance is not failure, it is intellectual honesty, and perhaps wisdom. Because it is in not knowing that wonder lives. Mystery keeps inquiry alive. Quantum physics already suggests that nothing is not empty, but a field of potential. Many contemplative traditions have long hinted that emptiness and fullness are two faces of a deeper reality. Perhaps the state from which our universe emerged was not simply nothing or something, but something that transcends both. To live with this mystery is not to live in confusion. It is to live in awe. Our knowledge is a small island in an immense sea of the unknown. And the joy is not only in mapping the island, but in standing at the shore, feeling the vastness beyond. The search for cosmic origins has no final destination. It expands us. It connects us to the universe and to one another through the shared, beautiful struggle to understand. From the first light to the beating of a human heart, the universe is not merely where we live. In some sense, it is what we are. If you're still awake, you can continue to the next chapter. Otherwise, I hope you sleep deeply and dream gently.